Hi, good morning. Let's get started. We're super happy to have Björn Hartman here from Berkeley, formerly at Stanford, and formerly at Google. He was with us last year for a good period of time working directly with our engineers and teams. This is the second one of our IoT series, the IoT Tech Talk series that Saurabh kindly pulls together. You're more than welcome to point new speakers, people that we should invite, etc. to him. We record the talks that only share internally, except if we mention that otherwise. So feel free to ask any questions. I don't think Björn is under NDA anymore, but he has a pretty deep understanding of what we're doing and how we are working. So don't spill any secrets, but do ask him questions that relate to your work. The idea is not last to see if some of the stuff that Björn is doing has a direct relation and can have an impact on your work. So I'm from University Relations. My name is Max Engels, and I organize the Jetsons IoT Research and Open Innovation Program. And the idea is to bring together internal expertise with external expertise, influence what he's doing, inspire him to bring some cool stuff into his lab, and the other way around. And without further ado, I turn it over to Björn. Thanks.
Great. Well, thank you, Max and Sarah, for inviting me. So I'd like to tell you a little bit, give you a cross-section through our work right now at Berkeley on design tools for IoT devices and applications. And since you're here sitting in on a talk on IoT, you probably don't have to spend a lot of time on diagrams like this, but just that we see a tremendous opportunity at this intersection of course, computing and networking tied to cloud platforms, but have that interact directly with the physical world through IoT products and devices. And I tend to think of the kind of devices that we see in our environment as falling into two groups. There's kinds of the head of the distribution, the couple of products that have captured popular mind share and sales, such as Nest thermostats or the Tesla, which is really a computer on wheels, right, with a big battery underneath. But then there's also, on the other hand, a really long tail where a lot of innovation is happening, where every week we see new smart health devices, home automation, pet trackers, gardening, etc. The list goes on and on and on. And having seen the explosion of innovation on the web, to me the question is, how can we enable a similar explosion of innovation and creativity in the IoT space? And so that leads me to the question, how can we rapidly design, prototype, and evaluate future IoT devices? To me, that really brings up another question, which is, well, what's the workshop, what's the work environment like that we want future IoT designers to operate in? And I think of this as the 21st century workshop, kind of going back to other important and famous workshops in the past that have enabled really transformative innovation. So think of the Wright brothers at the beginning of the century, who built their prototypes for airplanes in a workshop that had all of the tools of their prior job as bicycle mechanics. So lots of manual tools and mechanical power tools. And then forward a couple of decades, and you get Hewlett and Packard's garage in Palo Alto, which was their workshop for building amplifiers, instrumentation equipment that then gave rise to what we see in Silicon Valley today. So to me, going forward, the 21st century workshop has three core ingredients. That is powerful design software combined with digital fabrication tools and ubiquitous low-cost programmable electronics. So design software enables users to create detailed plans and code how their creation should look like and work like. And of course, this is where my own training as a computer scientist comes in, right? We create the software that lets users create better models. Now, what we're also seeing at the moment is something that's maybe not as rapid as Moore's Law, but we also see this curve in digital fabrication where hardware, manufacturing equipment that was previously in the millions of dollars and industrial sized is coming down in price and accessibility to the point where it's accessible to the individual designer and developer. Now, I'm not claiming that desktop fabrication is as powerful as what you would find in a factory in the US or in Shenzhen, but it gives you the leverage of actually building custom hardware yourself for very low capital investment. So the key point here is that digital fabrication will be used for many more tasks by many more people than traditional fabrication has been in the past. And then the third ingredient is just ubiquitous programmable hardware. So our microcontrollers sell now for $1 at even a quantity of 100, and even at a quantity of 1, you can get an embedded Linux system for $4 or $5. So the cost on the bill of goods of a new product of adding computation to it is basically going to zero. And so as a result, we have computation and communication appearing in all of our products. The age of the standalone device that you just go into a store and you buy the piece of hardware and maybe the embedded chip and that's it is already over because of those trends. All right, so those are the ingredients that I see in the workshop of the future, and that's not just a theoretical notion. So about 4 years ago, my collaborators, Paul Wright, Eric Paulus, and I started a small fab lab in the basement of the Citrus building in UC Berkeley called the Citrus Invention Lab, where we built and outfit an entire space around this combination of design tools, digital fabrication, and programmable electronics. And as of last year, we were able to grow this model from a single room in a basement to we now have a brand new building on UC Berkeley's campus, the Jacobs Institute for Design Innovation, that in many ways is kind of our playground for classes and projects in this space. So if you're in Berkeley's campus, I invite you to visit us. We have a very nice studio space for making and for teaching. And I just wanted to give you a brief overview of a couple of the types of projects that maybe a couple years ago were the realm of research in ubiquitous computing, but now, because of the advances in tooling, you can get a group of students to do those over over the course of 10 or 12 weeks. So here, for example, is a fixture-level water flow monitor. So we're in a drought in California, right? Water conservation is important. This is a little device that you screw in right in front of your shower head or a faucet. Inside it has a 3D printed impeller with magnets on the periphery, so when the water rushes through, the impeller starts to spin. That induces a current in a coil. That powers up a microcontroller, which uses a Hall effect sensor to measure how quick the thing is spinning, which measures the water flow and sends that to your phone. Another device of local interest, this is a fermentation monitor for wineries. So if you go up to Napa, that's a major industry. So it turns out fermentation is kind of a well-characterized process, but things can go awry, and if your fermentation for various impurities diverges from the ideal curve, you're flushing thousands of gallons of wine down the drain. So this is a small device that you just put in your tank. It has two high-sensitive pressure sensors, and the pressure differential lets you calculate the degree Brix, or the remaining sugar content in your fermentation tank. And so there's an expected curve, there's a measured curve, and then when you get the deviation, the device then sends a text message to the vintner who can head out and save the tank by adding sugar or other ingredients. We've also had some startups. Here's Dash Robotics. They worked in our lab. They make small bio-inspired foldable robots. So this is basically a sheet of composite cardboard and nylon that you fold up into a 5-gram robot. that then has a small PCB on board, so you control this robot from your phone or tablet. Here's a project that uses some Google hardware. So a group of students was really interested in using Google Glass to control the kinds of smart appliances that are starting to appear everywhere in our environment. So the idea was that you just look at a device, this lamp, and then when you tap, you get a custom UI for that device on your near-eye display. And so that was basically done by augmenting glass with a couple cent IR emitter. So you look at the TV, you tap, you get the control for your TV. You look at the fan, you get the control UI for the fan, etc. And maybe one more example. We also have students investigating what future smart power tools could look like. So the kinds of things you buy at Home Depot, right? Right now it's basically a motor on a stick. And so how can adding computation, sensing, and actuation help you there? So one of the devices students built here is, for example, an augmented drill that has cell phone distance sensors in the front, so it can tell the distance and the orientation that you're holding it to your work surface. And so it can give you, you basically can download instructions or a tutorial into your power tools, and it'll project instructions and gauge your performance in real time. Just another.
Drill provides interactive guides to help the user locate the correct drill.
All right, so a couple lessons learned. So we produce dozens of these projects every year in our institute. So a couple of the lessons learned. First, the trouble is really at the intersections of these different domains, right? So you're dealing with software, you're dealing with embedded electronics, you're dealing with the mechanical and also the industrial design to make one of these devices. And wherever two or more of these domains meet, that's where the trouble lies. Just looking at software alone, what we see is kind of a dominant architecture for many of these projects that we've called MGC, Embedded Gateway Cloud. So you're programming some embedded chip that talks to either your phone or a home gateway, but then really a lot of processing is also done in the cloud. And so you're programming this entire stack, which means 3 different platforms, probably half a dozen different languages, and just getting this up and running is really challenging for students. Another observation is these types of products, especially if you look at it not from a large company perspective like Google, but a small startup that has 2 or 3 people trying to build one of these products, is this gets prototyped into existence, right? Rather than kind of a long design and planning process ahead of time. So, and in particular, the design is driven by user and application considerations, which is right from a human-centered perspective, but the choice of technology is often kind of not an afterthought, but it's driven by what's accessible, what's productive, what's quick to get started with, and where's there a good community where you can get help online. So a couple of implications for tools from that. First, our tools should embrace iterative prototype-driven development, and tools for prototyping are not at all the same as tools for production. Right? The kinds of constraints or the kind of sweet spots they want to hit are totally different. One is robust, replicable, well-maintained. The other one is get me to something that runs as quickly as possible. And so you want to use the right tool at the right time. Second one that's also borrowed from the success of the web, right? Enable domain experts who really know something about a particular domain to be successful in creating at least a working prototype of a device to test whether that device has value for its actual end users. And then a last one is also, because this stack tends to be so complicated, we need better tools for just probing, understanding, debugging what's even going on when our IoT devices don't behave the way we expect them to. So I just want to give you 3 quick slices through concrete projects that we've done in our lab to support the prototyping of these types of IoT devices. And these projects, generally, we tend to focus on the maker community. So students, people working in hacker spaces, etc. So that puts some constraints on both the expertise we can assume that our users have and also the kind of equipment and resources they have access to. So let's start with software. So as I mentioned, many of the devices that we see emergent, both commercially and in our setting at Berkeley, follow this MGC architecture. So you have an embedded device that usually uses Bluetooth Low Energy or maybe ANT, some other low power protocol to talk to some gateway, which has a bigger battery, which has more radios, which can then in turn talk to the cloud. And user interfaces can be delivered either on the gateway device itself or through a browser in the cloud. Now, what we'd like to do is simplify programming across this stack. So clearly, you have to do something on the embedded device, right? You have to define what kind of services it offers, what kind of, for example, sensing it offers. And there has to be some application logic. But wouldn't it be nice if we could at least cut one of the three slices out and say you only provide code at the endpoints? So that's the idea behind Fabric. The idea is you either take off-the-shelf BLE devices or you have your own custom device that has some own custom firmware running on it. And then all the way at the other end, you write a web app that defines the UI and the application behavior. And then the platform basically fills in everything in the middle. So you run a custom gateway app on your phone or tablet or home gateway. That in turn talks to one of our own servers, and then the web app that shows the UI talks to our server. So basically what we have here is marshalling and translating between BLE and TCP/IP, and having a nice web API for programming BLE devices. So the way you program this is you take out your device, put it next to your phone, have your phone scan it, say, I want to write an app for this type of device. Then say my application uses the following collection of devices, and then we just drop you right into a web-based code editor where you then write code as if you were on the one hand, as if you were on an embedded device, so you can use BLE, Bluetooth Low Energy APIs right away. On the other hand, you can also use the whole web stack for talk to other web services or UIs. So concretely, what does that look like? Well, if you've ever worked with Bluetooth Low Energy, there's get, set, and notify are kind of the building blocks of Bluetooth Low Energy. And so now you're in JavaScript, and you can just query, get me a heart rate monitor, get me the heart rate monitor registered with this application, and just issue a get or a set, so a read or a write on that device. And so in between then, right, we post something to our server. That server queries, finds the right gateway that has seen the right wireless device, sends that request to that device, and then pipes it back up from the gateway to the cloud where it gets delivered back into your application. So that's the general approach. This definitely has some limitations, right? So every message that you send has to go from the cloud to mobile to your device and all the way back up. So this is not particularly efficient, but so this is maybe not the technology you would use for robust implementation that you ship. On the other hand, by simplifying the process, it is much faster for the developer to get up and going, writing their logic. I think debugging for this space is still a big open question. If something doesn't go right, where do you know, where is the problem? Is it in your client-side JavaScript code? Did you misinterpret the Bluetooth API? Did you make a mistake in your firmware? Where is it? Many different layers. So next steps we're taking in this direction is we're actually looking at distributed model view controller paradigms as ways of defining apps at a high level that then get partitioned over phones and devices and cloud in a more efficient way, and we're working on these runtime inspection and monitoring tools. All right, because these talks are short, I'm going to just move from project to project to project. Moving, yes?
I'm going to ask the question later anyway. You might address it
Okay.
in your talk already. Whenever you see you're using any Android, Google-related technologies where, it gets kind of interesting and easier for our folks to think about connecting to what you're doing. That would be helpful.
Yeah, so in this case, so we've written in Fabric, where would the Google technologies come in? Well, what's the gateway, right? What's the gateway running in your pocket? And so we've written gateways both for iOS and Android. So happy to talk with anyone about that later. Great. Okay, so now I'm going to shift gears and go from just the total software platform layer to, well, these devices also have some physical instantiation, right? So it's a physical, all IoT devices are a physical product. So how do we make defining the physical user interface and experimenting with it of these devices easier and faster? So the question here is, how can we make hardware prototyping as fluid and as fast as graphical user interface prototyping? So specifically here, we're looking at devices that have a physical user interface, such as game controllers, DJ interface, mice, flight simulator controllers, right? All of these have particular physical user interfaces because whenever it comes to virtuosity and performance, hand and brain co-evolved, so having a physical thing to touch and operate is preferable to just touching flat glass. So nowadays, you walk into any hardware lab, you'll find 3D printers being used extensively to prototype the look and feel of these types of devices. So I will print you a plastic shell that says, here's where a joystick would go, and here's where the buttons would go. Downside is, that's just plastic, right? It doesn't do anything. It just gives you a sense of the shape, but not of the functionality. If you actually want functionality, well, then you're dealing with electromechanical co-design. So now I'm designing the shell, but I also have to now fit a PCB in, and then how does the circuit board actually integrate with the shell, and where do all the components go? And this is the kind of detailed design that at some point you have to do and get right, but it's not what you want to spend weeks on during prototyping. So here's an alternative vision of how you could prototype the physical user interfaces of these devices. And that is, you 3D print your object, and then you just stick a camera inside of it. And you use the camera as a super sensor to do computer vision on the inside of the object and to detect all kinds of interactions with the device itself. So the idea here is, well, you already have a CAD model if you want to 3D print it, right? Because that's kind of the input to the 3D printing process. So we're going to take your CAD model and we're going to modify it directly in your CAD environment. So we're going to take your 3D model and then we add a virtual camera model. And that virtual camera model is designed to replicate all the pertinent parameters of a physical camera that we're going to use for sensing. So you stick the virtual camera inside, and then we can check, well, which of these different input affordances can that camera see or not? Well, usually it can't see all of them because the camera has a limited field of view. But then, because we haven't made the object yet, we can just change the model to make the camera see more of these input devices. So for example, if you have a button here on the side, and the camera blues the camera's field of view, can't see it, well, you can just extrude the geometry of the button to meet the field of view of the camera. So here, for example, is a dodecahedron input device where we can just extrude buttons to the inside so you can see all of them from a single camera. That doesn't always work. So for example, if you have something parallel with the optical axis, extrusion won't help you, but we can use just a little bit of computer graphics. Then we're going to ray trace on the inside of the object, and we're going to ray trace rays into the inside of the object reflected by the surface normal, and then we're going to look for reflected rays that hit one of our input devices with one bounce. Why would that matter? Well, that tells us if we put a mirror in that spot, you'll be able to see that device when you put a camera inside. So you can see in this photo, there's a mirror inside that lets you basically see around a corner and lets you see these buttons on the underside of the device. So this is basically all automatic processing that we do. You just design your device. We run an analysis over it, modify the geometry before you print it. And so then when you print it, you attach the camera. And then we just perform computer vision on the inside to track how all the different input affordances are moving. So this is the flip side of what computer vision usually does, right? Advances in computer vision usually say, let's come up with better algorithms so we can extract more information from an unknown scene. Here, we know exactly what the scene is because we created the 3D model. So we can use completely off-the-shelf object tracking from OpenCV, and we just modify the environment to make the computer vision problem easier. So we've built a variety of devices. Here's an ergonomic mouse. Here's, from my prior career as a DJ, we built a DJ controller and hooked it up to commercial DJ software. This approach doesn't always work. So if you have really narrow snaking geometries, then a single light bounce will not make everything visible. But we gave this technique to a bunch of mechanical engineering students, right? These are the people who have the necessary CAD skills, and they were all able, within a short time of maybe half an afternoon, to build these types of DJ controllers, and that would work with this sensing technique. So a way of maybe letting the mechanical and industrial designers in your team more rapidly try out different form factors and get interactive prototypes in a short amount of time.
What is the latency you have on the video recognition, the image recognition of the buttons? I mean, buttons you often associate with being very...
Right. So the answer to that is depends on what kind of camera you want to pick, right? So there's kind of the frame rate of the camera and then the additional latency from the recognition approach. We do very simple blob tracking. So you do a connected component analysis over the image. Doesn't have to be particularly high resolution. So I think overall we just picked a normal, 30 to 60 frame per second camera. So we ended up with that in the 80 to 100 millisecond delay. You could buy yourself a faster camera and optimize the blob tracking. So I think that you can shrink that down to, in musical instruments, like synthesizers, usually you want to get below 15 milliseconds or so for it to feel natural to be playing. And so it's not quite there yet, but I don't think there's a particular research barrier. It's more an engineering barrier to shrink that down. All right, so the key ideas here were use vision on the inside of a fabricated object, and then what makes this tractable is this co-design of geometry and sensing technique. Yes?
Generalized technique, like, is there any reason why I couldn't switch out the sensor and replace the camera with an IR sensor or something else like PLE?
So, right, so could it be wireless? Absolutely. We just picked the simplest thing to do wired USB. We have also I think the same conceptual technique also works with other types of physical phenomena that you want to sense. So what we, for example, also did was we used a contact microphone and put it on physical objects, and then we 3D print tiny tines, so like tines on a comb, underneath the input devices. So when you strike them, the tines, you can model their vibration properties, and you can basically infer what kind of sound you will hear when you strike them. So we've done it acoustically as well. OK, let me show you one last project. And this is kind of hot off the press. It's not yet published. We'll show this at WIST in October. And that is just helping people with the prototyping of their electronic circuits, especially novices. So before you send out for a board, that you get manufactured and assembled, right? Usually you start by prototyping circuits on a breadboard. Breadboards are amazingly flexible and fast, but there are a couple of well-known issues, such as they're kind of build-only devices. It's really hard to read the state of your breadboard after the fact. Loose wires, power issues, component polarity, many different problems can pop up, but they're very hard to troubleshoot and detect. So just in case, is everyone in the audience at least locally familiar with breadboards? Yes. Good. So how do you debug when something goes wrong on a breadboard? Well, traditionally, the approach is you do point-wise measurements. You pull out the multimeter and get a point-wise measurement, either a single one, or you pull out the scope and do it over time. Now, a point measurement actually requires that you already have a hypothesis of what's wrong, right? Because you say, I think it's that component, then you go measure that component. We actually know from research on programmers that non-experts are generally bad at generating reasonable hypotheses of what is wrong. So we're going to replace point measurements with ubiquitous instrumentation. Just measure everything all the time. And then combine these measurements with some model of what should be going on in your circuit. So here is our augmented breadboard. We call it the toast board. And as soon as you start making connections, we visualize both on the board and in a web client the voltage at every row of your board. And this currently, in this prototype, was still a little slow. It runs at about 100 hertz. And then when you add just little bits of information about what the circuit is that you're trying to build, now we can perform automatic checks. So for example, if I reverse this LED, we can automatically generate a warning which says there's something wrong with this LED. How do I know? The voltage drop across this LED is not what you would usually expect. So you either have it backwards or it may be blown. And we can do that for a range of different components. So discrete components, chips where we have the data sheet for, etc. How does this work? Well, we take your breadboard and we hook it up to a multiplexer scan chain where we just go row by row, scan the voltage at every row with as many ADC ports as we have available, feed that information back locally, but also send it on to a computer where we can give you a richer debugging IDE. And so the way we actually get to scan the breadboard is we peel the backing off and stick it with Z transfer tape onto a custom PCB, so we get connections to every row of the breadboard. Let me skip over that. So key ideas here is let's port ideas from software debugging, like constant background compilation and error checking in IDEs, and apply them for circuit construction. And then we have this basically database of component-specific checkers that embed domain knowledge, like datasheet specifications, and compare expected values to real-life data that you get. And there's a very clear next step, which is to jointly debug both the circuits and the embedded code simultaneously. All right, maybe let me wrap it up. So I showed you just a quick slice that goes from software platforms to industrial design to electronics, because the IoT stack, right, it touches upon all of these different domains. And a couple of takeaway messages. I think, you know, IoT devices, they do require this integrated approach to mechanical, electrical, and software design, and so our design tools should start to reflect that. Right now, the design tools really kind of treat each domain independently, and so working across these different domains, I think there's a lot of value to be unlocked. In general, prototyping tools let users describe goals at a higher level of abstraction, and then you let the tool or the platform take care of mapping goals to low-level operations. But there are two general principles at work. So sometimes you can black box things. So when the complexity is incidental, you don't want the user to know about the complexity, like bridging between Bluetooth Low Energy and TCP/IP. Then you just hide it in the platform. Let the platform do the right thing, and don't ever let the developer worry about it. On the other hand, when the complexity is inherent in the task, like do I have the right circuit constructed here, then you want to gather as much information as possible, visualize it in as rich a way as possible. And then finally, there's, I think, this real opportunity to leverage digital fabrication during prototyping and co-design the geometry of what you're printing with properties of the electronics you plan to put inside. So in our case, it was sensing through vision or acoustics. But I think there are many other places where this principle may apply. Okay, should point out that, of course, very little of that work was done by myself and was all done by fantastic students. And with that, I will thank you for your attention and open up to more questions.